Welcome back to You Revise, where we talk about everything exams. Let us take a look at question 12 from the 2017 exam. The question reads, a sealed glass tube at room temperature contains nitrogen dioxide, which is a brown gas, and dinitrogen tetraoxide, which is a colorless gas in equilibrium, as represented by the following equation, which is this one here. So we are told that this is brown. I'm going to label this, and we're told that this is colorless. If the appearance of the gas mixture at room temperature is pale brown, so this whole mixture is pale brown, obviously, because if you have a brown color, you add a colorless substance in there, it's gonna literally dilute the intensity of the brown color, right? Which one of the following is true if the glass tube is placed in hot water? Okay, we are supposed to select the correct answer from this list here, but as usual, it says it's our tradition. We need to look at what the examiner had to say about this question. 74% of candidates actually got this question right, which is pretty good. There are no other additional remarks from the examiner. Down here, I've got the syllabus points which inspired this question. The syllabus points read, the effect of changes in the concentration of solution and partial pressure of gases on chemical system initially at equilibrium can be predicted and explained by applying the collision theory to the forward and the reverse reaction. So what it's saying here is the collision theory can be used to predict and it can be used to explain. So the collision theory can do both things. The effects of changes in temperature, concentration of species in solution, partial pressure of gases, total volume, and addition of a catalyst on an equilibrium system can be predicted using Le Chatelier's principle. What it means is LCP can only predict. It's important for you to know that it's something that comes up in the examiner's report every time, that some students, when they're supposed to explain, they explain using Le Chatelier's principle, which is wrong. You can only predict using the Le Chatelier's principle. What I tell my students is, if you've got a question and they are not sure whether to use Le Chatelier's principle or the collision theory, I would use the collision theory, because if you use the collision theory, it covers you for both prediction, making a prediction, and explaining. But if the question is clearly saying explain, it means you're supposed to use the collision theory, right? And if the question is asking you to state what you will observe, which way equilibrium will shift, it's just asking you to predict, which this is where you use Le Chatelier's principle. Okay. Now, let's take a look at the question here. The answers read, the gas mixture will not undergo any noticeable change in appearance. The gas mixture will become darker brown. The gas mixture will become even paler at first, but then it will return to its original appearance of pale brown. The gas mixture will become colorless. Okay, we're going to look at this in a short while. Let me just clarify a few things. I've got these two axes here for drawing graphs. I'm going to illustrate this graphically for you, and then we look at which answer will actually match what we would have come up with based on the graph. Now, one thing I always ask my students is, when you are given that delta H is less than 0, delta H is greater than 0, what you need to do actually is to add this to the equation, because this one here shows us that delta H is negative, which means this process is exothermic, which means energy is a product. Once you actually do this, you can actually look at what happens to the system. For example, if we assume that we find this system at equilibrium, these are just like hypothetical values. You could do it whichever way, but you will still observe the same effects. So I'm going to say on this side here, I've got concentration. If you want, you can call it partial pressure. On this y-axis, I'm going to plot the concentration or partial pressure. And on this side, on the y-axis, I'm going to have time. The same thing here, I'm going to have on this side, I'm going to have a rate, and on this side, I'm going to do a time graph. So I'm going to try and illustrate this process, how the system is going to respond to this imposed change in terms of concentration or partial pressure, if you want to call it that way, in terms of concentration of components, and then we look at how that is going to impact the color. And then we talk about Le Chatelet's principle so that you can clearly see what's happening here. And when we find this system at equilibrium, we'll find this rate, the rate of the forward, which I'm going to represent with a red line, and the rate of the reverse, which I'm going to represent with the blue. These are just equal here, right there. Okay, the only reason why I've separated this so that we can see what's happening as we draw this for clarity purposes. Okay, now going back onto this first graph, we know that if we increase temperature, we are going to increase the amount of energy, because energy is part of the products. If I was going to use the collision theory, I would say I've increased the products on this side. If I increase the products, what's going to happen? This here, I'll see the frequency of collisions on this side is going to increase, right, compared to the frequency of collisions on that side. But because this is one system, if I increase energy, I'm also increasing collisions on this side, but there will be a lot more collisions on the product side than the reactant side. Why? Because energy is on the products. Now, so if I do this, the system is going to start responding. So what we're going to see happening on the rate time graph is both the forward rate will increase and the reverse rate will increase. We said the red one is the reverse rate, and the blue one is actually the forward rate of reaction. I'll represent that with F. The reverse rate, we said the frequency of collisions on the reverse rate on this product side is going to be much greater than the frequency of collisions on the on the reactant side. So this is going to see a greater increase. And on the reactant side, yeah, the rate of reaction or the frequency of collisions will also increase, because temperature in general increases the average kinetic energy of particles, but it impacts more the side that has the energy as part of the system. So how is this system going to re-establish equilibrium? The system is going to re-establish equilibrium. Since we've got a lot more collisions on this side, we're going to see the energy decreasing, because that's the purpose of that, because the system will try to oppose that imposed change and shift equilibrium towards reactants. And we'll also see a decrease in the concentration of dinitrogen tetraoxide. So what will happen is this rate here will decrease. The reverse rate will see that decrease, and we are going to see the forward rate increasing until it catches up with the reverse rate. Let me do this. So this one will decrease up to a certain point, and then we will see the forward rate also increasing like that. So this is what we are going to see happening here. Okay, I'm gonna draw this like that. I always prefer to do these as dotted lines first, so that I get the feel of where everything is going, and then I can just, go over the dotted lines to draw a proper graph. If it was on paper, my drawing would be much smoother than this. Okay, now if we look at it in terms of concentration, I've already said the concentration of dinitrogen tetraoxide is going to decrease, while the concentration of nitrogen dioxide is going to increase. So I'm going to assume, let's just assume that this is nitrogen dioxide. What made me actually decide this? Because it's pale brown. The fact that it's pale brown, it tells me that there is slightly more nitrogen dioxide. If the colorless was more, the brown color would be probably highly invisible. So yeah, that was my thinking. You could do it whichever way. Now, so we're going to see this concentration gradually increase like that. And like we said, the concentration of dinitrogen tetraoxide will decrease on the other hand. And this is what the concentration time graph will look like for these components. Now, let's look at the physical observations. If we increase the amount of dinitrogen tetraoxide, it means the brown color will also increase. We're going to see the solution, I'm not saying the solution, the mixture, because it's gases, sorry, the mixture becoming darker brown. Okay, now let's look at our answers to see what happens. Oh, well, before I go to the answer, for those of you who, I'm sure this will be where the majority of these students who got 74% would be, my aim is to catch those, the 26%. You might be the 26% now who tried out this question and you realize that you got it wrong. The aim for me going through all this is to capture the 26% and bring them on board and hopefully see that percentage go up to 100% if a similar question comes in the exam, of which it does. These questions are a permanent feature in your exam. You should be able to take a situation like this, scenario like this, and convert it or represent it as a rate time graph or a concentration time graph, partial pressure time graph. It doesn't matter. You should be able to work with both. As you can see, I could take this same question 12 and change it into a short answer or extended answer question. It doesn't really, there's nothing stopping me from doing that. So you have to be aware that whether you like it or not, there is either going to be a question where you have to use the Le Chatelier's principle, collision theory, draw these graphs, etc., make predictions, explain using this principle. So they are a permanent feature and they will be worth a few marks in your exam. Understanding and knowing how to draw this is very essential. Now, now that we know that the solution, why do I keep on saying solution? The mixture gets darker brown because these are gases in a way. Now, let's take a look at the answers here to see which one matches the explanations we've given here. The gas mixture will not undergo a noticeable change. No, the gas mixture will undergo a noticeable change because the brown color will increase, so it will get darker brown. Okay, the gas mixture will become darker brown. This is the correct answer we are looking for. C, the gas mixture will become even paler at first. No, it doesn't become even paler at first, right? Because as we can see, the collisions will all increase and we can't see, it's not going to become, we're not producing more of the colorless gas by increasing temperature. It's not going to happen that way. The gas mixture will become colorless. No, because we have agreed that the reactants will increase in concentration and the reactants have got a brown color, so there is no way the mixture will become colorless. So from this here, we can conclude that the correct answer is B. I shall see you when you attempt the next question. Thank you once again for watching. I shall see you in the next video. I hope this video was very helpful and I would love to hear any questions, any concerns, or anything that you think could have been done differently in this video.